All right, good afternoon, or whatever time of day you're watching this, Algebra 2 students. This lesson is over Skill 17, Exponential Growth and Decay. So I'm going to start with a couple of definitions. Exponential growth is a quantity that increases by a fixed percentage at regular intervals. Notice the key word here is increases. So we're going to have growth when that happens. And of course, the opposite of growth in our case will be decay. So exponential decay is a quantity that decreases by a fixed percentage at regular intervals. So let's look at some real life scenarios that come along with growth and decay. You might see things that say cases increase by 15% each day. Savings account balance with 5% interest compounded quarterly. The reason we know that's increasing is because you're putting your money into a savings account. And when they give you interest, that is money they increase your account balance with. And then home values appreciate. So the word appreciate means go up. So appreciate by 2% each year. Each of those, you'll notice that there was a regular percentage that was increasing each time, so therefore we called those exponential growth. And we'll talk about how to write those as an equation in a moment. Some examples you might see for decay, you might see a population decreases by 2% each year. A car depreciates in value, so depreciate is just the opposite of appreciate. So if a car depreciates in value by 10% each year, that means we're losing 10% of value each year. This is why people don't always buy brand new cars, because they depreciate so quickly. You might see a stock loses 0.5% of its value each week during a recession. Each of those talks about decreasing in regular intervals. Again, notice that we're talking about percentages. So that is why we're using exponential models here. So no matter what your exponential is, whether it's growth or decay, you're going to have an equation that looks like this. Y equals A times 1 plus R to the T power. That's if we have growth. If it was decay, instead of the 1 plus r, you would have 1 minus r. Okay, so we use this one for decay. All right, when you're looking at these are different than linear functions in the sense that we're not going to grow as a straight line like a linear function does, but rather we're going to start off slow and it's going to grow quickly. That's, of course, if it's growth. If it was decay, we would start here and we would slowly drop off. And you might remember this from the exponential functions lesson where you were graphing exponentials. So just to show you that, when you looked at that, you may remember also that your y-intercept was not a number at the end, but it was actually the a value here. So your a value is going to be your y-intercept. It's going to be your initial value. Growth or decay rate, r is that value. So no matter if it's growth or decay, the r is going to be that rate. And we want to make sure that that's expressed as a decimal if written as percentage. So make sure that if you have a percentage, you write that r value as a decimal. All right, so we're going to look at a few scenarios here. For each problem, we're going to model with an exponential function and then answer some questions. Example 1 says that a job with a starting salary of $40,000, that's our initial value. That would be the A in our function. The rate of increase, so R is 0.02, that's 2% as a decimal. The growth factor is going to be 1 plus r, so in our case 1 plus 0.02, which is 1.02. So if I wanted to answer the question of how much you would make after 10 years, I forgot to define t up above. T is going to be time. Should have made that note in the function. But if I wanted to model this with an equation, I would say y equals our a value of 40,000 times the quantity 1 plus r, so in this case 1.02, and we want to figure for 10 years, so we're going to raise it to the 10th power. 1.02 to the 10th power. We get a really long decimal, so what I'm going to do is not write that out, but instead I'm just going to put the 1.02 to the 10th power. I'm going to put that in the calculator first, and whatever that comes up with, I'm just going to hit times 40,000. And so we're going to get $48,759.78. That's going to be our answer. That would be our salary after 10 years if we assume that we're going to get a 2% increase of a raise each year. Now, you could probably round that up to the nearest dollar. Usually salaries are rounded to the nearest dollar, but it doesn't really matter. The next one, it says Sally is training for a 5K run, which is about 3.1 miles. And it says that she started on day 1 by running 0.25 miles without stopping. That would be our initial value. Her goal is to increase her mileage without stopping by 10% each day. So our rate would be 10% as a decimal, so 0.10. The growth factor, we are increasing her goal, so 1 plus r, so 1 plus 0.10, so 1.10. The question says, will she be able to run a full 5K after 30 days? So let's write our equation. So y equals a times 1 plus r to the t power. In our case, t is 30. We're going to do the exponent part first. We're going to take 1.10 and raise it to the 30th power, and then multiply that by 0.25, and we get about 4.36 miles. And the question was, will she be able to run a full 5K? Well, remember, a 5K is about 3.1 miles, so yes, she will. She'll be able to do that. All right, the next two examples will be of exponential decay. So the third one says a city of 500,000 loses 1% of its population each year. So the initial value is the 500,000 people that live in the city. The rate of decrease is 1%, so R is 0.01. So remember, you just take your 1%, move your decimal 2 back, put in a 0 for the placeholder. The decay factor is going to be 1 minus R, so 1 minus 0.01, which would be 0.99. And when we write this equation, it goes y equals 500,000 times 1 minus r, so 0.99 to the 10th power. In my calculator, I'm going to do 0.99 to the 10th. And then whatever that gives me, I'm going to multiply that by 500,000. And we're going to get 452,191 people. That would be the population after 10 years. All right, last problem. Dejan takes 20 milligrams of a drug to help with the symptoms of an illness. Due to absorption in the body, the drug loses 25% of its strength every hour. The drug will be effective until there are about 2 milligrams left in the body before needing another dose. What was our initial value? Well, we had 20 milligrams in the body, or in the drug rather. What is the rate of decrease? Well, we're losing 25%, so 0.25. The decay factor, 1 minus r, is how we figure that out. So 0.75. And now it says, will Dejan need another dose in 8 hours? So we're going to plug our pieces into our equation. And if our answer to this is underneath the number 2 milligrams, then we will need another dose. So 0.75 to the 8th power, and then I take that times 20, and we get about 2.00 milligrams. So yes, Dejan will need another dose. Okay. All right, so now when you come to class, we're going to talk more about exponential growth and decay, and you will have a chance to be able to practice some problems. So I'll see you then.